Okay, so let me next do a couple more examples. So this next example we'll do a factor relationship. So I'll say that xy is a point in my relation, is in R, if x is a factor of y. So let's just say that R is a subset of S cross S, where S is the numbers from 1 to 20. So if, by the way, how many possible relations are there on S cross S? 400. Okay, so S cross S has 400 points, right? It's 20 by 20. So the size of S cross S is 400 because it's 20 by 20. And a relation is a subset of S cross S, right? Yeah. How many possible subsets are there of S cross S? It's not factorial, it's the power set. 2 to the 400. So that's how many possible relations that we have. So possible relations R is somewhere in the power set of S cross S, right? It's one of those elements. And how many elements are there? 2 to the 400. So there are 2 to the 400 possible relations. This one is just one of them. The factor relation is just one of them. Okay, so what kind of points are in this relationship, if this is my definition? Well, we have the point 1, 1, because 1 is a factor. We actually have point 1 everything, right? Because 1 is a factor of all the other numbers. I'm just going to write like that for all the ones that have 1. And then we're going to have points like 2 what? 2, 2, 2, 4, 2, 6, all the way up to 220, right? And then I'm going to have what? 3, 3, 3, 6, all the way up to 3, what? 18. And then 4, 4, and so on. You can fill this thing out because you know how to do factors, right? We don't need to put all the points. It's just one example of a relation. We could have made it smaller and made it so we could draw it. Okay, so I'm going to do a smaller one with the factor. I'll just make a smaller set S. Divides and factor of is the same thing, right? Okay, so don't read divides and go, what's that? Or don't read factor of and go, because we've been working with divides and factor of all semester. So they're the same thing. So let's make S a little smaller. So R is in S cross S, and we'll just say S is 2, 3, 5, 6, 8, 16, and 18. Okay? So let's make this relation. So 2 divides itself. It also divides 6. It divides 8, 16, and 18. And then we'll do all the ones that 3 divides. 3 divides itself. And 6 and 18. 5 doesn't divide anything but itself. 6 divides itself. It also divides 18. 8 divides itself and 16. 16 divides itself and 18 divides itself. So that's the entire set.
R.
This is R. And it's a subset of S cross S. Okay, so let me give you some definitions, and then let's see which ones apply to this set. Okay, first of all, is this transitive? We already talked about transitive a little bit. If A divides B and B divides C, then A divides C would be true if this is transitive. Is it transitive?
Yes.
Yeah, because if 3 divides 6 and 6 divides something else, then 3 is going to divide the something else also, right? So this is transitive. And if you notice, every point divides itself too, right? So this is called reflexive because every number relates to itself. Like 2 relates to itself. So every number in here, every number in S relates to itself. It's not irreflexive because it's reflexive. So is it symmetric? So symmetric would be if 3 2's in there, then 2 3 is in there.
It's not symmetric.
No.
It's not symmetric, right? Is it asymmetric?
Yes.
Trick question. It's not asymmetric
Can you flip the door?
because it has 2 2 in there, and 3 3, and 4 4, and 5 5. It has all of the reflexive points. And asymmetric means if I have a point in there, I can't reverse it and still be in the set. So 2 2 can be reversed and I'll still be in there, so it's not asymmetric. There is a property where as long as nothing else can be reversed except for those, that's called antisymmetric, and this set is antisymmetric. So it's the same as asymmetric, except it doesn't mind that you have 2 2 in there.
You said not symmetric. What did you mean?
This is not a symmetric set. I'm going to give you definitions for symmetric and everything, and they're also in packet 5, which is, it's on the web. It's just not moved up from old, but it's the same. So I'll move it up today or tomorrow. I'm going to give those to you in just a minute, all the definitions. I'm trying to get you just thinking, like, when you see the word symmetric, what do you think?
Okay.
Okay? So you're using your knowledge you got before you got here, which is plenty.
So reflexive and asymmetric are mutually exclusive?
That's right. These are mutually, I can't be both reflexive and asymmetric at the same time. And actually, part of the definition of asymmetric is that it's irreflexive. So it can't be reflexive and asymmetric at the same time. Unless it's empty. It can be both if it's empty. If the relation is the empty set, but we don't usually deal with those. Let's see, reflexive, symmetric, transitive, asymmetric. I think that's pretty much everything I wanted to do. So this kind of acts like less than or equal to, right? In a way. Divides is not the same thing as less than or equal to, but it's acting like it, right? If one number divides another, then, and so if A divides B and B divides C, then A divides C. And it's working just like less than or equal to, because it's also reflexive, right? If 2 divides itself, I can reverse that. It's still in the set. It's antisymmetric just like less than or equal to. So 2 is less than or equal to 2, but if 2 is less than or equal to 3, I can't put 3 is less than or equal to 2. So it's kind of like less than or equal to. So the way it's like less than or equal to is that it has these 3 properties: transitive, reflexive, and antisymmetric. And when it has those 3, it's called a partially ordered set. And it's called that because we can think of a minimum in this set, or minimal elements in this set, or maximal elements in the set.
Does this relate in any way to implication, since it's less than or equal to?
It's just like that too. So implication has the same 3 properties, and it's also a partially ordered set. So one set that's ordered is the numbers. Right? Numbers are ordered. This is partially ordered because I can't always compare two numbers. That's why it's called partially ordered. So I don't actually have a comparison between 8 and 18 in this set. I don't have 8, 18 or 18, 8. So I don't necessarily have a relationship between every pair. But if you take every pair of regular numbers, I can tell whether one's less than or equal to the other. That's a full ordered. This is a partial order because I can't compare every set, every pair of numbers.